In this video, we're going to take a quick look at the radioactive decay data Earth Science reference tables, including a very brief discussion over what radioactive decay actually is. Let's begin by taking a look at the chart itself, which can be found on page 1 of the New York State Earth Science reference tables and downloaded in the description below. Let's begin with the definition. Radioactive decay is the natural breakdown of an unstable radioactive element into a stable element. All you need to understand for this basic video is that in nature, certain elements exist in an unstable form, and they go through the process of decay to become more stable. What's interesting about radioactive decay is that it happens at a predictable or knowable rate. And that's what makes it useful for determining the age of an object that contains the radioactive element. This predictable rate is known as a half-life, and it's going to become very important to using carbon dating or any sort of radioactive decay to figure out the age of different materials in nature. Let's go back to that chart. Now, you'll see the chart shows 4 common radioactive isotopes on Earth. These are all useful for dating the various ages of different materials, from the oldest rocks to more recent organic matter. Let's zoom in and look just at the first row, which is carbon-14. So that first column labeled radioactive isotope, that's where you'll see the name of the radioactive element itself. The second column, labeled disintegration, shows the parent isotope, which in this case is carbon-14 or C14, and the daughter, which is what it will decay into or what it will turn into over time. And in this case, carbon-14 decays into nitrogen-14. And then finally, the third column, labeled half-life, shows the number of years that it takes for half of your original radioactive substance to decay into the daughter product. So in the case of carbon-14, every 5,700 years, half of your original carbon will have decayed into nitrogen. Now, to really wrap your head around this, it's best to look at an example. So let's dive in with a little simulation here. We're going to look at this land mammal known as a woolly mammoth. This extinct creature died out in the recent past, and so as such, we are able to often find bones and fur and other remains of them frozen in ice around the Earth. And the nice thing is that these organic materials, like bones and fur, will contain carbon-14, as essentially all organic matter on Earth does. And so we can use that carbon-14 to figure out precisely how old a woolly mammoth was when it died. So let's go back to our chart for a minute, and we'll see carbon-14 is listed as the top radioactive isotope here. And this is an appropriate isotope to use in dating a woolly mammoth because its half-life of 5,700 years is appropriate for what we know about when the mammoth went extinct. Now, what we're going to do is actually play out the decay process half-life by half-life and see what happens to the amount of carbon-14 and the amount of nitrogen-14 that we have. And so here we have this little decay dashboard, which essentially shows the same thing, but it shows it in 4 different ways. In this top left quadrant, we have a table that's going to show row by row what's happening, how much time has passed, how much carbon has decayed, how much nitrogen has grown, etc. In the top right, we just have a visualization that shows with these little colored rectangles the relative amounts of carbon-14 and nitrogen-14 over time. Bottom right, we have a line graph that's going to show the decay and growth of carbon and nitrogen. And the bottom left, we have a simple pie chart showing the relative amounts of each. And so let's get started. So with row 1 here, 0 time has gone by, 0 half-lives, 0 years. And so we have all of the original carbon-14 that was in this woolly mammoth bone. And let's just say, for argument's sake, it was 256 atoms of carbon-14. Now, that's not really accurate to nature, but we're trying to use simple numbers to understand the process here. So we'll start with 256 of carbon-14, And since none of that has decayed yet, we have 0 nitrogen-14. We have 100% of our original carbon, and you can see that in all the different visuals here. But what if we fast forward 1 half-life? Now, 1 half-life has gone by, which for carbon-14 is 5,700 years. And let's look what happened to the amount of carbon. We have cut it in half from 256 atoms down to 128. Now, those 128 that decayed didn't disappear, but rather they turned into the stable daughter product, nitrogen-14. So now you see we have equal amounts of carbon and nitrogen, 128 atoms of each, meaning we also have 50% of that original carbon. And so you can see that in the top right, where we have essentially equal amounts of yellow and pink, equal amounts of carbon and nitrogen. And the bottom right, you can see that at this moment, the pink line has dropped from 256 to 128, and the yellow line has grown from 0 to 128, and the two lines actually meet at this point. And this is the only time in the decay process when you will have equal amounts of the parent and the daughter. And of course, you can see that as well in the pie chart. But let's keep the process going. Let's fast forward a second half-life. Now, another 5,700 years have passed, so a total of 11,400. We cut our carbon in half again, from 128 cut in half to 64. Those 64 atoms, again, didn't disappear, rather they decayed into nitrogen. So the amount of nitrogen has increased. And you can see that clearly with the rectangles. We have more yellow or nitrogen now and less pink carbon. And you can see with the line chart, the nitrogen, the yellow line is increasing and the pink line is decreasing. Fast forward another half-life, another 5,700 years. Now 17,100 years has gone by. Cut that carbon in half again down to 32. Make those 32 that change turn into nitrogen. Nitrogen is up to 224. And you can get the idea that we have less and less carbon and more nitrogen. We just keep cutting that carbon in half time after time after time. Fast forward again, 4 half-lives, 22,800 years, and now we're getting down to very little carbon left and a lot of nitrogen. Again, 5 half-lives, 6 half-lives. At 6 half-lives, nearly 35,000 years have gone by, and we're down to just 4 atoms, or 1.5625% of the original carbon. And so you get the idea that over time, less and less of the parent, more and more of the daughter. But what do we actually do with this? So to understand how you would work with this information, let's look at a sample question. So here we go. Scientists infer that early North American humans hunted the mastodon. Carbon-14 dating of the rib bone indicates that 2.4 half-lives have passed since the mastodon was killed. Approximately how many years ago did the mastodon die? So just to understand, we have this mastodon, which is a relative of the woolly mammoth, actually, and it died, and we want to figure out how long ago it died. So first thing we have to do is identify what radioactive isotope we're using, and it tells us in the question to focus on carbon-14 dating. We also know that 2.4 half-lives have gone by. By looking at the chart, I can see that 1 half-life is 5.7 times 10 to the third, or 5,700 years. And if I have 2.4 of those half-lives, I simply need to multiply. 5,700 years times 2.4 half-lives equals 13,680 years. Now, luckily, it's a multiple choice question, so I'm going to choose the best answer, and clearly that would be 13,700 years. So by looking at the amount of carbon-14 within this bone, we can determine the approximate age of the mastodon, or the number of years ago when it actually died. Let's look at a second question. This one says that the graph below shows the radioactive decay of rubidium-87. What percentage of rubidium-87 atoms are left after 4 half-lives? So again, the key is, let's look at what we're talking about. We're talking about rubidium here, which decays into strontium, and a half-life is 4.9 times 10 to the 10th years. And we want to know how much of that rubidium will be left after 4 half-lives. And specifically, we're looking at a percentage here. So I'm actually going to move away my chart for a second, and we're going to pull in a simple pie chart. Starting with 0 half-lives, at that point, we have 100% of our rubidium. Fast forward 1 half-life, and we have 50% of rubidium and 50% of its daughter product, strontium. Fast forward to 2 half-lives, we're down to 25% rubidium. 3 half-lives, we cut it in half again, we're at 12.5. And then finally, after 4 half-lives, we're down to 6.25% rubidium. As a side note, you can also tell this from the chart itself by looking at where 4 half-lives crosses the decay curve and going to the left, and you will see that it's about 6.25%. And so that is your correct answer. So hopefully this helped you gain a little bit of insight into how radioactive dating and decay works. Thanks for watching.